We start off building our explanation by drawing a diagram. To the left you will see a blue rectangle which represents the rubber. In the center of the screen you will see a graph. At the very central point represents the rubber uncompressed, but if you were to squeeze the rubber it would resist, and that resistance is shown as the graph rising up to the left. If you were to pull it apart, it would also resist, and that resistance is seen as the graph rising off to the right. If we took a whole series of snapshots of the rubber band and the outside world and record on the graph for each snapshot the energy and actual position, we'd get some of the following features that we see here. The outside world would get a lot of positions at low energy, and as we increase energy, be fewer. That's just statistics. In the graph that represents the rubber band, because of quantum mechanics, there's only a certain amount of allowed energy levels, so we wind up drawing these as distinct lines. Stretching the rubber band is represented by the elongated red rectangle off to the right of the graph, and not surprisingly, the potential energy curve narrows, represented by the red curve to the right. And as you can see, the particles or the states in the system have their energy increased, and when they collide with the outside world, the energy gets exchanged and we feel this as heating up. This upper energy level diminishes. There's less states in this level, and when the rubber band relaxes, this level drops down again and it's unpopulated, so energy from the outside world falls inward and it feels cooler. You can explain the phenomena of a rubber band cooling when it relaxes by many different ways. Expansion and compression of gas, entropy, but I like the quantum mechanical model because it gives you the deepest insight into why the temperature changes.